When determining the appropriate panel size for track lighting, several factors must be considered to ensure safe and efficient installation. Firstly, you must perform a load calculation to determine the total amperage required by the track lighting system. This involves estimating the total wattage of the track lighting, which is based on the wattage of each fixture multiplied by the number of fixtures. Once you have the total wattage, you can convert it to amps using the formula amps equals watts divided by volts. In the case of a 208Y/120 volt service, the voltage used in the calculation is 120 volts. With the calculated amperage, you can determine the size of the electrical panel needed to accommodate the track load, keeping in mind several key considerations. One consideration is the amperage capacity. The panel must have sufficient amperage capacity to handle the total amperage of the track load. To account for future growth or additional loads, it is advisable to add a 20% margin of safety. The next thing to consider is the number of circuits. You divide the total amperage by 15 or 20 amps, depending on the circuit breaker rating, to determine the number of circuits required. You should provide at least one circuit for the track load. Another consideration is the panel type. It may be useful to use a sub-panel dedicated to the track load to isolate it from other electrical systems. Select a panel with the appropriate number of circuit breaker slots and wire size capacity. Lastly, code requirements is something that you must comply with local electrical codes and regulations regarding panel size and circuit protection. For example, consider a scenario where you have 1100 feet of track with fixtures consuming a total of 5,500 watts. To convert this to amps, you would divide 5,500 watts by 120 volts, which equals 45.83 amps. Adding a 20% margin for safety, you would multiply 45.83 amps by 1.2, resulting in 55 amps. Then, dividing by 15 amps, the value for 15 amp circuit breakers gives you 55 amps divided by 15 amps, which equals 3.67 circuits. Rounding up, you would need 4 circuits. Therefore, you would require a sub-panel with at least 4 circuit breaker slots rated for 15 amps or higher. In conclusion, the optimal panel size for a 1100 foot track load with a 208Y/120 volts service would be a 4-circuit sub-panel rated for 60 amps or more. This provides ample amperage capacity, multiple circuits for flexibility, and compliance with code requirement. When selecting a circuit breaker, several factors come into play to ensure proper protection and functionality within an electrical system. Firstly, the amperage rating of the breaker must be carefully considered. The breaker's amperage rating determines the maximum current it can safely carry before tripping and interrupting the circuit. This rating should be matched to the ampacity of the circuit wiring and the load it serves to prevent overheating and potential fire hazards. Secondly, the voltage rating of the circuit breaker is crucial to match the voltage of the electrical system it will be installed in. Using a breaker with a lower voltage rating than the system voltage can result in failure, while using a breaker with a higher voltage rating is generally acceptable as long as it meets other requirements. Thirdly, the interrupting capacity of the circuit breaker is another critical factor. The interrupting capacity, measured in amps, indicates the maximum fault current the breaker can safely interrupt without failing. It should be equal to or greater than the available fault current at the breaker's location in the electrical system. Next, the type of circuit breaker is another consideration. There are various types of breakers available, including standard thermal magnetic breakers, ground fault circuit interrupters also known as GFCI breakers, and arc fault circuit interrupters known as FSI breakers. The appropriate type depends on the application and the specific protection requirements. For example, GFCI breakers are required in wet locations to protect against electrical shock, while FSI breakers are used to detect and interrupt arc faults, which can be a common cause of electrical fires. Also, the trip curve characteristics of the circuit breaker influence its response to overcurrent conditions. Circuit breakers have different trip curves that define the relationship between the magnitude of the overcurrent and the time it takes for the breaker to trip. These curves are designed to coordinate with the characteristics of the protected equipment and minimize nuisance tripping while still providing adequate protection. Lastly, compliance with industry standards is essential. Circuit breakers should comply with relevant industry standards such as those set by Underwriters Laboratories, also known as UL, or the National Electrical Manufacturers Association or NEMA, to ensure safety and performance. These standards specify requirements for testing, construction, and labeling of circuit breakers. When installing a subpanel, you should consider several factors to ensure safety, compliance, and optimal performance. Firstly, the location of the subpanel is something to think about. Choose a location that is accessible, dry, and free from obstructions. The subpanel should be mounted on a stable surface and located close to the point of load to minimize voltage drop. Secondly, the size of the subpanel needs to be appropriate. Determine the total load requirements of the circuits that will be served by the subpanel. Select a subpanel with sufficient capacity to accommodate the existing and future loads, with some extra capacity for expansion. Thirdly, the wiring and overcurrent protection also need to be considered. Use appropriately sized conductors and overcurrent protection devices, circuit breakers or fuses for each circuit in the subpanel. Follow the National Electrical Code known as NEC guidelines for conductor ampacity, overcurrent protection, and grounding. The NEC requires that all circuit breakers and fuses be properly labeled to indicate their purpose and amperage rating. Fourthly, grounding and bonding needs to be done properly. Establish a proper grounding and bonding system for the subpanel to minimize the risk of electrical shock and ensure proper operation of overcurrent protection devices. Connect the subpanel's grounding bus to the main panel's grounding electrode conductor, and bond all metal enclosures and equipment to the grounding system. Fifthly, circuit identification and labeling is important. To clearly label each circuit breaker or fuse in the subpanel to indicate the area or equipment it serves. Maintain an accurate circuit directory to facilitate troubleshooting and future modifications. Sixthly, compliance with electrical codes is key. Adhere to all applicable electrical codes and regulations when installing the subpanel. Obtain necessary permits and inspections from local authorities to ensure compliance with safety standards. Lastly, professional installation if needed. If you are not comfortable working with electrical systems, consider hiring a qualified electrician to install the subpanel. A professional electrician can ensure that the installation is performed safely and correctly in accordance with code requirements. A 208Y/120 volts electrical service is a type of three-phase electrical system commonly used in commercial and industrial buildings in North America. This system consists of 3 hot wires, a neutral wire, and a ground wire. The voltage between any two of the hot wires is 208 volts, while the voltage between any hot wire and the neutral wire is 120 volts. In a 208Y/120 volt system, the Y configuration refers to the way the 3 phases are connected. The 3 hot wires are connected in a Y shape at a common neutral point, hence the name. This configuration allows for both 208 volts 3-phase power and 120 volts single-phase power to be supplied from the same system. The 208 volts 3-phase power is typically used for larger loads such as motors, HVAC equipment, and machinery, while the 120 volt single-phase power is used for lighting, receptacles, and small appliances. One of the advantages of a 208Y/120 volt system is its versatility. It can supply both 3-phase and single-phase power, making it suitable for a wide range of applications. Additionally, the lower voltage of 120 volts is safer for general-purpose use compared to higher voltages such as 240 volts or 480 volts. Another advantage of a 208Y/120 volt system is its efficiency. The 3-phase power distribution reduces current flow and minimizes voltage drop compared to single-phase systems, resulting in lower energy losses and improved overall efficiency. When working with a 208Y/120 volts electrical service, safety precautions must be followed to prevent electrical shock and other hazards. Only qualified electricians should perform installation, maintenance, and repair work on these systems. It is essential to de-energize circuits before working on them and to use appropriate personal protective equipment such as insulated gloves and safety glasses. In summary, a 208Y/120 volts electrical service is a versatile and efficient three-phase system commonly used in commercial and industrial buildings. It provides both 208 volts three-phase power and 120 volts single-phase power, making it suitable for a wide range of applications. However, safety precautions must be followed when working with these systems to prevent electrical hazards. When determining the number of circuits needed for a track lighting installation, several factors must be considered to ensure proper functionality, safety, and compliance with electrical codes. Firstly, calculate the total load. Determine the total wattage of all the track lighting fixtures that will be installed on the circuit. This can be found on the fixture labels or in the manufacturer's specifications. Secondly, determine the circuit amperage. Divide the total wattage by the voltage of the circuit to determine the total amperage required. For a 120 volt circuit, the formula is amps equals watts divided by 120 volts. Thirdly, consider the circuit breaker rating. Determine the amperage rating of the circuit breaker that will be used to protect the circuit. Common circuit breaker ratings for lighting circuits are 15 amps and 20 amps. Fourthly, calculate the number of circuits needed. Divide the total amperage by the circuit breaker rating to determine the minimum number of circuits required. Round up to the nearest whole number to ensure adequate capacity. Fifthly, account for voltage drop. Consider the length of the circuit and the gauge of the wire being used. Long circuits with undersized wires can experience voltage drop, which can cause lights to dim and reduce the efficiency of the system. Consult the NEC guidelines for voltage drop and adjust the number of circuits or wire gauge as needed. Sixthly, consider future expansion. If there is a possibility of adding more track lighting fixtures in the future, it is advisable to provide additional circuits to accommodate the increased load. Seventhly, separate control. If different sections of the track lighting need to be controlled separately, provide separate circuits for each section. This allows for greater flexibility and energy savings. Lastly, comply with electrical codes. Ensure that the number of circuits and wiring methods comply with all applicable electrical codes and regulations. Consult with a qualified electrician or electrical inspector if you have any questions or concerns. For example, if a track lighting installation has a total load of 1800 watts on a 120 volt circuit with 15 amp circuit breakers, the total amperage required is 1800 watts divided by 120 volts, which equals 15 amps. Since the circuit breaker rating is 15 amps, only one circuit is needed. However, if the total load was 2400 watts, the total amperage required would be 2400 watts divided by 120 volts, which equals 20 amps. In this case, two 15 amp circuits or one 20 amp circuit would be needed. In conclusion, determining the number of circuits needed for a track lighting installation requires careful consideration of the total load, circuit breaker rating, voltage drop, future expansion, separate control, and compliance with electrical codes. It is always best to err on the side of caution and provide additional circuits to ensure adequate capacity and safety. When selecting the appropriate wire size for an electrical circuit, several factors must be considered to ensure safe and efficient operation. Firstly, you need to determine the ampacity of the circuit, calculate the total current that the circuit will be expected to carry. This is typically determined by adding up the wattage of all the devices or appliances that will be connected to the circuit and dividing by the voltage of the circuit. Secondly, consult the NEC ampacity tables. The NEC provides ampacity tables that list the allowable ampacities for different wire sizes and insulation types. These tables take into account factors such as conductor material, insulation temperature rating, and installation conditions. Thirdly, correct for ambient temperature. The ampacity of a wire decreases as the ambient temperature increases. If the circuit will be installed in a hot environment, you may need to use a larger wire size to compensate for the reduced ampacity. Fourthly, account for conduit fill. If the circuit conductors will be installed in a conduit, the number of conductors in the conduit can affect the allowable ampacity. The NEC provides guidelines for directing conductor ampacity based on the number of conductors in a conduit. Fifthly, consider voltage drop. Voltage drop occurs when the voltage at the end of a long circuit is lower than the voltage at the source. Excessive voltage drop can cause lights to dim and appliances to malfunction. To minimize voltage drop, you may need to use a larger wire size. Sixthly, choose the appropriate insulation type. The insulation type of the wire should be selected based on the environmental conditions in which the circuit will be installed. Common insulation types include THHN, THWN, and XHHW. Lastly, comply with electrical codes. Ensure that the wire size and installation methods comply with all applicable electrical codes and regulations. Consult with a qualified electrician or electrical inspector if you have any questions or concerns. For example, a 15 amp circuit that will be installed in a dry location with an ambient temperature of 30 degrees Celsius. According to the NEC, 14 American wire gauge or AWG copper wire with THHN insulation has an ampacity of 15 amps. However, if the ambient temperature is higher, you may need to use a larger wire size to compensate for the reduced ampacity. In conclusion, selecting the appropriate wire size for an electrical circuit requires careful consideration of the ampacity of the circuit, the NEC ampacity tables, ambient temperature, conduit fill, voltage drop, insulation type, and compliance with electrical codes. It is always best to err on the side of caution and use a larger wire size to ensure safe and efficient operation. When designing a track lighting system, there are several key considerations to keep in mind to ensure optimal performance, aesthetics, and energy efficiency. Firstly, determine the purpose of the lighting. Consider the primary purpose of the track lighting system. Is it for general ambient lighting, accent lighting, task lighting, or a combination of these? The purpose will influence the type of fixtures, beam angles, and light levels needed. Secondly, plan the layout. Determine the layout of the track lighting system based on the architecture of the space and the areas you want to illuminate. Consider the placement of furniture, artwork, and other focal points. Thirdly, select the appropriate track type. There are several types of track systems available, including single circuit, 2-circuit, and 3-circuit tracks. Choose the track type that best suits your needs in terms of flexibility, control, and load capacity. Fourthly, choose the right fixtures. Select track lighting fixtures that are appropriate for the purpose of the lighting. Common fixture types include spotlights, floodlights, pendant lights, and linear lights. Consider the beam angle, light output, and color temperature of the fixtures. Fifthly, consider the light source. Choose the appropriate light source for the track lighting system. Options include incandescent, halogen, fluorescent, and light-emitting diode, also known as LED lamps. LED lamps are generally the most energy-efficient and long-lasting option. Sixthly, calculate the light levels. Determine the appropriate light levels for the space based on the activities that will be performed there. Use a light meter to measure existing light levels and calculate the additional light needed. Seventhly, control the lighting. Consider how the track lighting system will be controlled. Options include dimmers, switches, and lighting control systems. Dimmers allow you to adjust the light levels to suit different activities and moods. Lastly, comply with electrical codes. Ensure that the track lighting system is installed in compliance with all applicable electrical codes and regulations. Consult with a qualified electrician or electrical inspector if you have any questions or concerns. For example, if you are designing a track lighting system for a retail store, you may want to use spotlights to highlight merchandise displays and floodlights to provide general ambient lighting. You may also want to use dimmers to create different lighting scenes for different times of day or special events. In conclusion, designing a track lighting system requires careful consideration of the purpose of the lighting, the layout of the space, the type of track and fixtures, the light source, the light levels, the lighting controls, and compliance with electrical codes. By taking these factors into account, you can create a track lighting system that is both functional and aesthetically pleasing. When working with electrical systems, personal protective equipment or PPE is essential for protecting yourself from electrical hazards. Firstly, insulated gloves are needed. Wear insulated gloves that are rated for the voltage you will be working with. These gloves provide a barrier between your hands and electrical conductors, preventing electric shock. Secondly, safety glasses or goggles are needed. Wear safety glasses or goggles to protect your eyes from arc flash, sparks, and other debris that can be generated during electrical work. Thirdly, a face shield is needed. Use a face shield to protect your face and neck from arc flash and other hazards. Face shields are especially important when working with high voltage equipment. Fourthly, flame-resistant clothing is needed. Wear flame-resistant clothing such as long-sleeve shirts and pants made from materials like Nomex to protect your body from burns in the event of an arc flash. Fifthly, insulated footwear is needed. Wear insulated footwear with non-conductive soles to prevent electric shock. Avoid wearing shoes with metal parts or soles. Sixthly, a hard hat is needed. Wear a hard hat to protect your head from falling objects and other hazards. Hard hats are especially important when working in construction or industrial environments. Seventhly, hearing protection is needed. Use hearing protection such as earplugs or earmuffs when working in noisy environments to prevent hearing damage. Lastly, voltage testers are needed. Use a voltage tester to verify that circuits are de-energized before working on them. Always test the tester on a known live circuit before and after testing the circuit you will be working on. In addition to using PPE, it is also important to follow safe work practices such as de-energizing circuits before working on them, using lockout/tagout procedures to prevent accidental energization, and maintaining a safe working distance from energized equipment. For example, if you are working on a 480 volts electrical panel, you should wear insulated gloves rated for at least 500 volts, safety glasses, a face shield, flame-resistant clothing, insulated footwear, and a hard hat. You should also use a voltage tester to verify that the panel is de-energized before starting work. In conclusion, using PPE and following safe work practices are essential for protecting yourself from electrical hazards. Always assess the risks before starting work and use the appropriate PPE and procedures to minimize the risk of injury. Local electrical codes and regulations play a crucial role in ensuring the safety and proper installation of electrical systems. Firstly, they establish minimum safety standards. Electrical codes and regulations set minimum safety standards for electrical installations to protect people and property from electrical hazards such as electric shock, fires, and explosions. Secondly, they cover wiring methods. These codes and regulations specify the types of wiring methods and materials that are permitted for different applications. They also provide guidelines for conductor sizing, overcurrent protection, grounding, and bonding. Thirdly, they address equipment installation. Electrical codes and regulations outline the requirements for the installation of electrical equipment such as panels, circuit breakers, receptacles, lighting fixtures, and appliances. They specify clearances, mounting methods, and other installation details to ensure safe and reliable operation. Fourthly, they require inspections. Many jurisdictions require electrical installations to be inspected by qualified electrical inspectors to ensure compliance with codes and regulations. Inspections help to identify and correct any deficiencies before the system is energized. Fifthly, they mandate licensing. Electrical codes and regulations often require electricians and other electrical workers to be licensed or certified to demonstrate their knowledge and competence. Licensing helps to ensure that electrical work is performed by qualified individuals who are familiar with applicable codes and regulations. Sixthly, they promote uniformity. Electrical codes and regulations promote uniformity in electrical installations, making it easier to design, install, inspect, and maintain electrical systems. Uniformity also helps to reduce confusion and errors. Seventhly, they are updated regularly. Electrical codes and regulations are updated regularly to reflect new technologies, best practices, and lessons learned from past incidents. Staying up to date with the latest codes and regulations is essential for ensuring safety and compliance. Lastly, they vary by location. Electrical codes and regulations can vary significantly from one jurisdiction to another. It is important to consult with local authorities and qualified professionals to determine the specific requirements that apply to your project. For example, the NEC is a widely adopted model code in the United States, but individual states and municipalities may have their own amendments or supplements. Similarly, in Canada, the Canadian Electrical Code or CEC is the national standard, but each province and territory may have its own variations. In conclusion, local electrical codes and regulations are essential for ensuring the safety and proper installation of electrical systems. They establish minimum safety standards, cover wiring methods and equipment installation, require inspections, mandate licensing, promote uniformity, are updated regularly, and vary by location. It is important to consult with local authorities and qualified professionals to determine the specific requirements that apply to your project. When planning for future growth in an electrical system, several factors must be considered to ensure that the system can accommodate the increased load without compromising safety or reliability. Firstly, assess current and future loads. Conduct a thorough assessment of the current electrical loads and estimate the expected future loads based on anticipated growth or expansion. Consider factors such as new equipment, increased occupancy, and changes in usage patterns. Secondly, determine the service capacity. Evaluate the existing service capacity to determine whether it is sufficient to handle the future loads. Consider the size of the service entrance conductors, the rating of the main service disconnect, and the capacity of the utility transformer. Thirdly, evaluate the panel capacity. Assess the capacity of the electrical panels to determine whether they have enough available breaker spaces and amperage capacity to accommodate the future loads. Consider adding subpanels or upgrading existing panels if necessary. Fourthly, review the branch circuit capacity. Evaluate the capacity of the existing branch circuits to determine whether they can handle the future loads. Consider adding new circuits or upgrading existing circuits if necessary. Fifthly, account for voltage drop. Consider the impact of the increased load on voltage drop. Use appropriately sized conductors to minimize voltage drop and ensure that equipment receives the proper voltage. Sixthly, ensure adequate grounding. Verify that the grounding system is adequate to handle the increased load and protect against electrical faults. Consider upgrading the grounding system if necessary. Seventhly, comply with electrical codes. Ensure that all electrical work complies with applicable electrical codes and regulations. Obtain necessary permits and inspections from local authorities. Lastly, plan for flexibility. Design the electrical system with flexibility in mind to accommodate future changes and additions. Use modular components and leave room for expansion in panels and wiring systems. For example, if you are planning to add a new wing to a building, you should assess the current electrical loads and estimate the expected loads for the new wing. You should also evaluate the service capacity, panel capacity, and branch circuit capacity to determine whether upgrades are necessary. In conclusion, planning for future growth in an electrical system requires careful assessment of current and future loads, evaluation of service and panel capacity, review of branch circuit capacity, accounting for voltage drop, ensuring adequate grounding, complying with electrical codes, and planning for flexibility. By taking these factors into account, you can ensure that the electrical system can accommodate future growth without compromising safety or reliability.